think maybe we'll just get started for now, and have folks join as they can. But welcome everyone. Excited you're all here. If you want to put your name and where you're joining from in the chat, I think it's always just nice to know where folks are coming from today. We're excited to kick off the new year with GreenStep and our coffee chat, Lakeside chat. So we had these last year. The idea is that we have some folks come to present on a topic and then leave a lot of time for questions. So please, as John is talking today, please put some comments in the chat. We'll make sure that you can all speak if you want to unmute yourself too, but we'll have folks monitoring the chat if you want to put anything in there. This is a kickoff too of our GreenStep Year of Water. We have a water challenge that we can put in the chat too. So as you're taking actions toward water this year, the idea is that we're collectively all working on water in some way or thinking about water this year. We will have topics that aren't related to water, but our focus this year is on water. So we're excited, and I'm delighted to have John Vanyo joining us today from MnTAP, and he's going to talk about some opportunities and that MnTAP has and what MnTAP does in general, so related to wastewater. So I will pass it over to you, John, and let you take it away.
All right, excellent. Thanks so much, Erica. Good afternoon, everyone, and welcome. Thank you so much for joining. Got a great presentation for you today. Presentation today is MnTAP Assistance and 10 Years of Wastewater Optimization. So my name is John Vanyo. I'm a senior engineer with MnTAP, and I'm pretty excited to kind of tell you a little bit about what our group is, what we do, a little bit about wastewater optimization, and then I'm also going to talk a little bit about our intern program. So at the very end, I'm actually going to share with you, I mentored 3 students last summer. And so I'm going to share a little bit about each of their projects and kind of what an intern project looks like in case maybe some of you might be interested in hosting one this upcoming summer. Okay, so my group is the Minnesota Technical Assistance Program. Our primary function is that we work with industrial manufacturing facilities on process efficiency types of projects. So these can be anything from energy efficiency to water conservation, fuel savings, safer chemicals, waste reduction, and kind of like everything else in between. I describe what we do in 3 main cores. So our first core is general technical assistance. So this is where we provide no cost, non-regulatory, confidential technical assistance to Minnesota businesses. Usually this is in the form of a site assessment where we'll come out and then we'll meet with either the plant manager or the maintenance manager or the environmental manager. And we'll kind of just like talk through which processes might have opportunities for resource conservation. And then we'll kind of actually go out on the floor, we'll collect information on the process, on the equipment, and then we'll take all of that back to our offices. We'll run our lit review, we'll run our calculations, and then we'll develop a nice recommendation letter for our site contacts to kind of summarize what the pollution prevention opportunities are that we found. And then finally, we'll actually have a report out meeting with our clients to talk through those findings, make sure they make sense, and also talk through potential next steps to actually get from what's on paper to actually like something implemented in real life. That's the goal. Our second core then is our intern program. So every single summer we hire about 15 to 20 engineering and science students. Usually these are upcoming juniors and seniors. And we place them on site in Minnesota businesses for 3 months over the summer to work on these types of pollution prevention projects. So we do scope these projects ahead of time. And actually, it's probably a good time to mention, January is sort of like our final month to find company projects. So if you happen to have a project, now is the best time to let us know, and we can come out and scope the project and help figure out how to make it successful. After January, then we get right into our like starting to hire our students and train our students so that they're ready for the summer. The intern program is extremely successful, and it's where most of our results come from. So it is a great place to kind of partner with MnTAP. And then finally, our final core is special projects. So these are going to be our grant-funded projects where we're competing for funding to either do a deeper dive into some of our core focus areas or it lets us do a little bit of work more on the periphery of, whether or not we'd have resources to do it otherwise is unclear, but with these special projects, we can do it. And so that's where this work on wastewater treatment efficiency comes in. Okay, so I do want to get into wastewater optimization. So I want to start here with just like wastewater 101. I know people have different levels of understanding of like the wastewater treatment process. When I started in MnTAP, I knew nothing. So I want to make sure everyone is sort of on the same page as we get into this discussion. So we start at the top left here. Wastewater comes in, our influent comes in, and we send it through screening and grit removal. So the idea here is we're trying to remove any like large solids so they don't plug up the processes downstream. Next, we're going to send our wastewater through a primary clarifier. Now, these are optional. Some sites have them, some sites don't. But the idea of the clarifier is we're slowing down our water so that we can settle out any small solids and then have mostly just water going to our next step. So our next step here is secondary aeration. So this is the core treatment process in most mechanical wastewater plants. The idea here is we're using very large industrial blowers or sometimes other equipment, but the idea is we're trying to send a bunch of oxygen into this tank. And so we're sending air through diffusers to make little bubbles, and we're bubbling air up into this tank. And then the idea is we're growing microbes at the same time in this tank, which can use that oxygen to break down the waste as a food source, and out of the tank will come clean water. So these little microbes, we're feeding the microbes, and in turn, the microbes are cleaning our wastewater, which is great. Then after aeration, our water, pretty much every plant does have a secondary clarifier, where again, we're slowing down the water, we're settling out any small solids, and we're also settling out the microbes here. And then finally, our clean water is going to go to disinfection and then go to the river. Meanwhile, then our solids that we've settled out here and here are going to go to the digester. However, you'll notice there is this little line here. So we recirculate some of these microbes back to our aeration tank, just so that we can keep a healthy microbial population here, so that we can continuously treat the water. We don't wash out our microbes. And then the solids that we've settled out. Now, when I say solids, these are still mostly water. You're probably right around maybe 3% solids, maybe up to 10 if you do some pressing of your solids, but it's still mostly water, but it's a little bit thicker. And so we need another treatment process to fully stabilize these biosolids. And so we do that in the digester. It can be done aerobically or anaerobically. So we can do it similar to aeration with air bubbles, or we can do it without any air and instead using heat and mixing. And if we do it this way, then we can actually create renewable natural gas, which is kind of cool, but we're not going to get into too much depth on that in this presentation. And then once our solids are stable, they go to stable storage. And then ultimately, many plants are land applying as fertilizer here in Minnesota. But some plants are doing other things like incinerating biosolids for energy, or some plants end up having to send their biosolids to landfill. But this is kind of the idea. This is the wastewater treatment process 101. And so with that, we will move on to how do we save energy here? So the main place that we focus in our projects was secondary aeration. And the main reason is because this process uses most of the energy in the wastewater plant. We talked about it on the last slide, but it is the core treatment process, right? So this is where our microbes are using oxygen to break down waste. Oxygen is supplied by huge blowers, usually. We make fine bubbles. And then very importantly, we have something called a DO probe, or dissolved oxygen probe, where we can measure the oxygen concentration in the water, which gives us a really nice, easy way to very quickly understand kind of how efficient this process is from a high level. At this point too, it's probably worth zooming out for 1 second. So this presentation as a whole is on wastewater, but in my work, I work with all kinds of industries and businesses, right? And so the processes that we use here don't just apply to wastewater, they can apply to other places too. So the idea of the reason we're focusing here is because this is where most of the energy is. For almost all of our projects, especially our intern projects, we're basically benchmarking is the first step. Is like we need to know where is most of your water being used so we can figure out how we can help you save water, or where's most of the energy, or where's most of the waste. That's a really, really good strategy to figure out like where you should focus your effort. And then there's another piece that I'll talk about in a moment. So we'll zoom back in, talk about wastewater, and talk about how much air do we need. So in this process, our blowers are adding oxygen at a certain rate into this tank. That's going to drive oxygen up. And then our microbes are going to consume oxygen and break oxygen down, driving oxygen levels down, right? And so when we combine those rates, if your residual oxygen is above zero, your microbes have enough oxygen to break down the waste. But typically, we're going to keep our residual oxygen level a little bit higher than that. And this will give us a little bit of a buffer. The point of the buffer is if we get like what's called a slug load from industry, let's say like there's a cleaning process at one of your food processors and they send a lot more waste than normal. You want your system to be able to react before it runs out of oxygen. So you want those blowers to be able to turn up, send more air to treat more load. And so having a little bit of buffer is good. The other reason why it's okay to do that here is because it's harder to add oxygen to your water the more oxygen that's already in it. So going from an oxygen level of 1 to 2 is relatively easy, whereas going from like a 5 to a 6 is much harder and needs much more energy. So this is relatively energy inexpensive to have a bit of a buffer. Okay. So then the other question worth asking here is why is there so often opportunity to reduce DO? You know, when I started doing this project about 10 years ago, it was about every single plant we went into had oxygen concentrations that were much, much higher than 2 milligrams per liter. And at the time I was so confused and I didn't understand it and I didn't know what was going on. And it really took me a while to get it. But the reason for this is because wastewater plants are usually designed with about 30 years of city growth in mind. And this is very intentional and it's by design. So like if you're on the city council, you know, you can't just build infrastructure to meet your needs today. You need to meet your needs today. Plus, you want to have room for your new businesses and your tourists and your new people to come into your town. And so in order to do that, you have to build your infrastructure to be a little bit bigger than you need it today. And essentially what that means is if you're an operator and you go in and you turn on your equipment, it's going to work. It's going to treat your wastewater, but it's going to have much more treatment capacity than you need today. So the final question here is then, well, what do we do about it? How do we actually save the energy? We know what the issue is. How do we save it? So there's a few methods we typically use in the project. The first one and the main one is something called a variable frequency drive. So the idea here is you can connect this to your motor and your motor blower system. And this allows you to essentially just turn down the speed. So instead of just having your blower be on off, now you can have it running at 80% speed or 60% speed or whatever you need it to run at. Usually for positive displacement blowers, and I'm not going to get into the details here too much, but usually you can go down to about 50% speed with a VFD, which is quite useful and can help you save a lot of energy. Now, sometimes a VFD isn't going to be the right option. Either there's not, the main reason why it wouldn't be enough option is if there's not enough turn down on the VFD to get your oxygen level where you want it. And so you're still, even with a VFD, you're still using way more energy than your process actually needs. In that case, sometimes the best option is to actually put in a smaller blower. And you still need to leave your other equipment there and it needs to be ready to go because you need to be able to treat your design load, but a smaller blower can sometimes pay for itself when the equipment is really oversized. Another pretty relatively common option, something that we've seen a few times at least, is at wastewater plants, you'll often see sites will have 3 blowers and 2 of them are on at any given time and the third one is redundant. And sometimes when we run the math on the amount of air that's needed, we find that they can actually get away with running 1 blower on and 2 blowers as being redundant. And that can be like a very nice low or no cost way to save a bunch of energy when it works. So this little table just shows the savings that we found from secondary aeration projects over the past 10 years. Now, only about half of that time we were doing energy projects, the other half we were doing nutrient projects. But you can see like some pretty nice implemented savings numbers, about 5.8 million kilowatt hours per year and about $450,000 per year of cost savings. So definitely some good opportunity that we found here in Minnesota. Okay, so that's what I have on energy. I'm going to move along now to nutrients. So this was kind of how we spent probably the other half of our time in wastewater treatment, was looking at biological nutrient removal. So before I get into that, I do want to talk about just what are nutrients and what is nutrient pollution. So when we talk about nutrient pollution, wastewater, we're specifically talking about nitrogen and phosphorus. These are both agents of growth. And so the idea is if you send too much nitrogen and phosphorus into a body of water, it will essentially cause your algae to grow and outgrow the carrying capacity of the body of water, choking out the oxygen and creating what's known as a dead zone. And we would like to avoid that. And so we would like to ideally treat for nitrogen and phosphorus and reduce this nutrient pollution. For me, I need things like this to be real. Like I can hear about it, but until it's real, it doesn't resonate with me. And so this is a picture from the mouth of the Mississippi River. This was taken years ago, but it shows the massive algal bloom that is actually there right now, that as we work towards reducing nutrient pollution, we are directly contributing to resolving this issue. And I don't have pictures of them, but they're also, I mean, we also feed some rivers up to Canada that are having the same issues. And so like this nutrient pollution issue is a problem and something that, we can help to fix. Okay, with that, we're going to talk about removal methods for both phosphorus and nitrogen. So for phosphorus in a wastewater plant, there's two ways to remove it. The first way is chemically. This is the most common way used right now, and pretty much every wastewater operator is going to be familiar with this. The idea is you add a chemical. This is going to come in a liquid form, and you're either going to add ferric chloride or aluminum sulfate. And usually this is done right before the secondary clarifier. And what happens is your metal, so either your iron or your aluminum, is going to bond to your phosphate in the water, and that's going to settle out the phosphorus for you. So it's relatively straightforward, relatively easy, but it does have two downsides. Downside one is you're basically constantly dosing chemical, which means you are continuously buying chemical to replace that chemical you're using. So it's expensive. Issue number two is if you'll notice the ferric chloride, there's this chloride piece. That means if we're adding this, we're adding chlorides into our water, which isn't great. It's not something we want to be doing. And if we're adding aluminum sulfate, we're adding sulfates into our water. Again, not necessarily something we want to be doing. So yes, this way it works. It helps us treat for phosphorus, but if we could do it another way, it could be better. So the other way that's available is biological nutrient removal. I'm going to explain it in a little more depth in a couple slides, but the quick version with this is we can create a condition in one of our treatment tanks where we will grow this organism, and then this organism will uptake phosphorus for us, very similar to how chemical would uptake phosphorus. It is a little trickier, a little more finicky, and we'll talk about that too, but that's the idea. Okay, next I want to talk about nitrogen removal methods. So for nitrogen, we don't have a nice chemical option. There's no chemical bullet here. I did lit review. I tried to find how could we possibly remove nitrogen from wastewater. I'm sure there's a way. I couldn't find it, which to me suggests either it's too toxic or it's too expensive for anyone to actually use. So the only way to remove nitrogen is biologically. Luckily, at least from my perspective, this is a little bit easier than the phosphorus. So the first step here is we need to, well, let me back up. We generally assume most of the nitrogen in our wastewater plants transforms into the form ammonium NH4 as it's coming into our plant. The first step to removing nitrogen is to convert that ammonium NH4 into nitrate NO3. And that's going to happen in aerobic conditions. So in our secondary aeration tank, we talked about this already. Everyone already has one of these. This process already happens. So most plants already are converting their ammonium into nitrate, they have this NO3 step. So the next step to get to nitrogen removal is we need to send water with containing that nitrate backwards into a tank with no oxygen, an anoxic tank. And that will allow the microbes that want oxygen to take it off of the nitrate and release the nitrogen gas. And that's called denitrification. So I have some diagrams to show this, and we don't have to go into a ton of depth, but that's the idea. Okay. So this is the same diagram we showed before, but this is just showing you where the BNR, the biological nutrient removal tanks, would go, right? So you would end up putting them between the primary clarifier and the secondary aeration tank. You'd have two tanks here, and then the secondary aeration tank is part of this process as well. So these are the three tanks you would want. You want an anaerobic tank, which you can think of as your phosphorus tank, an anoxic tank, which you can think of as your nitrogen tank, and then an aerobic tank, which is everyone already has again, but this is where we break down our BOD and break down our NH4. So I'm going to talk about each of these pretty briefly, but I'm going to actually start with tank 3 here and we're going to work our way backwards. And the reason for this is because if you'll notice, there's a recirculation loop from tank 3 to 2, and then there's a recirculation loop between tank 2 and 1. And that's following the recirculation loop is just the easiest way to understand what's going on. So starting in tank 3 here, this is again our aerobic tank. We already have this tank. We have oxygen in here. Our BOD is getting broken down, and we're breaking down our ammonium into nitrate. This is already happening. Great. Key thing to take here is in this process, we are recirculating water containing nitrate back to our anoxic tank. Okay, so let's go to the anoxic tank now. In this tank, we're not adding any oxygen, but we are, again, sending this nitrate back. So what's going to happen here is our microbes, they want oxygen. They can't get it from the water because there's none in the water, but they can pull it off of this NO3 and make nitrogen gas. That's exactly what they're going to do. And that is how you get denitrification. If you need nitrogen removal at your wastewater plant, this is the process the plant's going to do. Relatively straightforward. Okay. Then if you want to go to get phosphorus treatment, you're going to need one more tank, usually. And so then you're going to send another recirculation loop or line back to what we call our anaerobic tank. And keep in mind now, this water we're sending back doesn't have oxygen in it, and it's not going to have much nitrate either because we just treated for that. So there's really very little oxygen at all. Okay, so then this is the final tank here is our anaerobic tank. And it's the first tank we see after influent. And that's important because anaerobic microorganisms are what we want to grow. The specific one is a PAO, a polyphosphate accumulating organism. This is the one that will uptake phosphorus for us. But in order to get it to grow, it requires these anaerobic conditions. And the main reason, the easy explanation is the aerobic microbes will outcompete the anaerobic microbes. It turns out if you can use oxygen for your respiration processes, you work faster, you move faster, you do things faster. So we specifically need a tank with no oxygen and a lot of BOD, a lot of influent waste to get these things to grow. But as long as we grow them, then as long as we give them the conditions to grow, they will grow. And they're going to, once we have the concentrations that we want, they're going to just flow through our process all the way back to our aerobic tank. And the last thing happening here is in aerobic conditions, these anaerobic microbes we grew are going to uptake that phosphate for us right before the clarifier, and then they'll be able to settle out in the clarifier. So that is BNR in a nutshell. If I lost you, I apologize. It is a little bit dense, but we're gonna go into get more fun conversations coming up here. So last thing to mention here, though, is there is a complication with biological phosphorus removal. And that complication is these organisms uptake phosphorus in aerobic conditions, but then they re-release it in anaerobic conditions. And I didn't explain it much. This is more of like the 201 topic, but as a wastewater operator, often what you're doing with your solids is you're basically trying to consolidate them and remove water from them. And when you remove that water, you send that water back to the head of the plant. And if your phosphorus happens to have released before you do that, you end up sending a bunch of phosphorus back to the head of your plant. So that can be an issue. Now, this isn't something I studied in depth. I know there are plants who have figured this out, how have those PAOs hold on to that phosphorus for them all the way through their process. And I know that there are other plants that end up doing something called side stream treatment, where they're taking this very high concentration of phosphorus water and treating that more efficiently in order to get the phosphorus out of it. But again, I'm not an expert in all the details here, so I apologize. But it's worth knowing that this isn't quite as easy as I would wish it were. But that's it. I guess the last thing to mention here too is there is a software program for biological nutrient removal, or there are a couple of them. My team used ASIM, Activated Sludge Simulation Model. There's also BioWin. But these are great. They let you model your whole plant. They let you model all your flows in and out, all of your recirculations, and it can help you tune your treatment process to get whichever nutrient you want to treat for. It can help you do that. Something we learned over the course of our project is a typical plant doesn't have enough food for the microbes to get full treatment for phosphorus and full treatment for nitrogen. So oftentimes you can either get some treatment of both or really good treatment of one or the other. And this kind of modeling software can help you figure out where you want to be and how you want to use your limited energy supply you have to give to your microbes. Okay, so that's what I have for wastewater. On the energy side, keep your dissolved oxygen at 2 milligrams per liter. You'll save a bunch of energy. On the BNR side, recirculate back to an anoxic tank. You can get nitrogen removal. Recirculate back to an anaerobic tank. You can get phosphorus removal. And you can use software to help you kind of figure out the details of the configurations. Okay, cool. Let's move on to the intern program. Thank you for sitting through that piece. I know that was a little dense. Some of the wastewater operators love it, but I know this group may or may not have. But anyway, more fun topics coming up. So these are results from our 2024 intern program. You can see our students, they do great work. They do awesome work. They save tons of water, energy, gas, waste reduction, almost $2.5 million of potential cost savings. Usually about 1/3 of what we recommend gets implemented at MnTAP, but that still represents a really nice chunk of change for these businesses who are part of our program. So what I want to do here to kind of wrap things up is I want to just tell you a little bit about the 3 intern projects that I mentored last summer. I had tons of fun mentoring these projects. They're great. The students are great. The sites are great. They're a lot of fun. And so I kind of want to just tell you a few minutes on each of them. Okay. The first project was with MnCore Industries. So this is an industrial laundry facility. It's located at the Faribault Correctional Facility. So the idea here is they employ 73 people, 62 of whom are incarcerated persons, IPs. And it really gives these people a nice opportunity to get some work experience prior to getting back out into the real world. They provide laundry services for about 27 clients in the area and process, 3.5 million pounds of laundry per year. So that's a pretty big workload that they have. Okay. So the project that we worked on. So Richard and I went up to the site to try to figure out, okay, how do we help them make this process more efficient? And the main thing we found is the site uses high pressure steam to heat the washers and heat the dryers. So they need a lot of heat for this process, of course, so they use steam. Great. What we found is that once you've used the heat from the steam, you make high pressure condensate, then you need to flash that, you need to remove the pressure from it and turn that into low pressure steam. And this is supposed to go to a heat exchanger so we can recapture that heat value and send that condensate back to the boilers. Unfortunately, at this site, this heat exchanger wasn't functioning. And so this low pressure steam, it was just going out the window. It was fascinating to visit and watch this, actually. So the project was twofold, right? One, we wanted to figure out what's wrong with the heat exchanger. Can we fix it? And two, what's the potential saving in terms of like steam and heat and water and chemical for getting this fixed? And so that's exactly what Richard did. And what he ended up finding is, so the steam plant right next door to this laundry facility is the steam plant where they're generating the steam. He found an identical heat exchanger in that steam plant that had been functioning for all these years. The one difference is that the other heat exchanger had a pressure release valve, and this one didn't have one. And so we suspect that the pressure just built up, blew a gasket, and it just had never worked properly ever since. So Richard was able to go through, he was able to run the numbers on this heat exchanger and found it was a little over 400,000 gallons of water per year, almost 33,000 therms per year of fuel, and about 11,700 pounds of chemicals they would save by basically being able to reuse that condensate and not have to redose that with chemical for annual savings of about $32,000, 1.5 year payback. Very, very cool. I'm just going to talk about the main projects I have my students work on, but you can see they always have like additional projects they're working on too in the background. So in this case, he also helped them kind of spec out some new, more efficient washers and also like lean their pressing and washing process. So a lot of great things happening with this project. Moving along, the second project I worked on was with the Hennepin Energy Recovery Center. This is our big waste energy facility in downtown Minneapolis. Generates electricity to serve over 25,000 homes. That was fascinating to me. I had no idea it was that much energy. So the projects we worked on here, I specifically remember scoping this project because we kept talking about like the common efficiency opportunities, and it was like, oh, they've already done that. They've already done that. That's already efficient. That's already efficient. Great. And the final thing we were able to find was within their cooling tower loop, we decided to dig into their cycles of concentration. And so essentially like the overview here is for this kind of process. So we're creating energy through incineration here, right? And so we need to cool down the equipment with cooling water just to make sure it like doesn't melt, it doesn't like deform, and it stays within like useful parameters, right? So we use a bunch of cooling water for that. And then to keep the water cool, we send that water into a cooling tower, some of it evaporates, and that cooling effect cools the rest of the water. Now you can imagine as you evaporate water out of a cooling loop, you're going to concentrate any minerals in that water. And that will continue becoming more and more concentrated until you balance it out with something over here called blowdown. So then we're basically going to send some water and also the concentrated minerals out of our system to wastewater. And that will create a balancing point called our cycles of concentration. So how many more times concentrated are our minerals relative to where they came in? And so what Xavier was able to do is we had done some work on cooling towers before, and we thought we might be able to boost the cycles of concentration just by a couple points, maybe a few points. And it's such a huge site that would save a lot of water and a lot of chemical. And Xavier was able to work with their team and work with their chemical vendor to figure out how much. And that's what I'm going to show you here. So this increasing the cycles of concentration ended up saving them 12 million gallons of water per year and 50,000 pounds of bleach per year for annual savings of about $50,000 in a 0.3 year payback period, which was so cool. It was so great to find, especially on a project like this where we went in not knowing what we were going to find exactly. It was so great to find this much savings potential. And then Xavier was also able to help them get their stormwater reuse system back up and running properly to save another 1 million gallons of water per year. And he found a way to reuse water from their newest piece of equipment, a new chute cooler, had single pass cooling water, and we were able to reloop that back into their cooling loop as well. So very, very cool water savings project here. And then the final project that I mentored last summer was with Bailey Nurseries. So this is a wholesale plant nursery. They basically grow potted plants for landscaping purposes. And they have facilities all over the place: Minnesota, Illinois, Georgia, Oregon, Washington. We, of course, just worked with the facilities in Minnesota. And our project, so Claire and I worked on this project, and our project was to help them figure out how do we save irrigation? How do we reduce irrigation water to save water? And it was so interesting because all summer, like we kept developing ideas, and we had a project team with folks from Bailey as well. And we were kind of like brainstorming, and we learned like there are different water classes, you know, A, B, C, D. And so some plants need more water, some don't need as much. And we kind of got through that. And then eventually near the end of the project, we realized all of these plants are potted plants. And what that means is that the amount of water you can add at any one time is limited by the size of the amount of soil in that pot. And we noticed that a lot of the baseline irrigation settings we're having more water than we would want kind of running through the bottom of those pots. And so we were able to do our calculations based on pot size and amount of soil to get the correct amount of water such that you do want a little bit of leachate coming through your pot, but not too much. And that's all. And then those plants that needed more water, we would have to water them more frequently to make sure they got the water they needed. But this was great. And Claire was actually able to do a side-by-side test in their greenhouses, one group of plants with their baseline settings and one group of plants with their new settings. And she was able to show by like weighing the mass of the different plants that there was no significant difference between the two settings, which was awesome. And so this project had huge savings. So for the greenhouses, it was 4.8 million gallons of water savings per year. And then when we applied the same math to, they have like acres of outdoor potted plants they're growing as well. The savings here was about 115 million gallons of water. So some huge water savings here. And again, it's a really nice, fun project to work on last summer. So that's kind of what I have for you. Thank you so much for having some coffee here and hanging out with me. Does anyone have any questions?
Yeah, perfect. Thank you, John. This is great. I don't see any questions in the chat yet, but please feel free to put them in the chat or raise your hand or just unmute to ask questions. I was going to ask a question. I was curious about, so like if a city is interested in like applying for one of these interns, how much information would they need to know? Like, can they be like, we know who our high volume users are. We know that maybe there's some nutrient reduction that could happen at this place. Is that enough information, or do they kind of have to come in mind with like a specific project ready?
Well, I mean, you can come with whatever you have, whatever makes sense to
Okay.
you. So basically, there's a couple ways we can do intern projects, right? So typically, our most typical intern project would be like we would actually find a company that wants to work on, like, let's say water conservation, right? So we would like do that. However, we might sometimes we'll work with a group, like maybe it's a city, and maybe they just want us to do a handful of assessments with some of their higher water users, and maybe we can do something like that. So there's different ways we can structure projects. But I will say, so like the first step is on our website, there's a place to just apply. So you just can fill out an application, or even easier, if you just want to email me, you can just email me. And what we're going to do, our first step is we're going to set up basically a scoping meeting with the applicant where we can kind of like sit down and talk through like, okay, what's the potential project? We can brainstorm it. And if it's a full idea, great, like we can run with it. But if it still needs to form, like we can help it form. Like our teams are pretty good at that too. So kind of whatever makes sense to folks will work. I should probably also mention, so our intern program is the only place where we do ask for a little cost share. So we ask for a $4,000 cost share from our partners. And this is just really to make sure that the sites partnering with us are invested, because we are like hiring an intern and placing them on site. So we want to make sure that like, there's some investment there. We do pay our students much, much more than that $4,000 for their work over the summer. And the projects themselves cost a lot more than that, but there is a little cost share for that. So I should mention it.
So our program mostly works with city staff and or elected officials and community leaders, some of which have their own wastewater treatment facilities. And I believe, right, MnTAP also, can support them in their own operations, even though they're not necessarily for-profit business industrial sector.
Yeah, we can. So we can support wastewater plants a little bit. In the past, most of that work has been through special grant-funded projects, which we currently don't have any. Well, I have one to work on a special project, but I didn't talk about. Maybe I'll talk about that in a minute. But so in general, I can do a little bit, but also at this point, I have connections with Minnesota Rural Water Association. So if they're a small town, I know who to send them. I also have connections at the MPCA. There's a new wastewater technical assistance team, and like they are very good at what they do too. So yeah, like if you've got a wastewater plant that wants some help, you can ask me, and I will either help them or I'll find someone who can.
Perfect. And so, the staff and folks that we work with in communities are often very close and connected to the businesses and industry that obviously are within their boundaries. And so this is, something that's helpful, I think, for folks to know that exists so that we can be getting information out there to the industries within their communities that MnTAP is here to help improve their efficiencies. And so obviously we can send them to the website. And I think I've seen some flyers from MnTAP over time, but in general, we can just have folks reach out to you and learn a little bit more about what, options might exist. Cool.
Yeah, that's perfect.
Awesome. Any other questions? Feel free to raise your hand or use the chat. I have another one that came to mind only because Erica and I were chatting over lunch today. Data centers keep coming up in conversations. And so just looking at some of the examples that you worked with last summer, I saw some maybe parallels of how data centers might utilize water for their cooling needs. So I would assume that that's something MnTAP might have in mind.
Absolutely. Yeah, we actually, two of us just took a data center efficiency training very recently in the last couple of months, just so that we were kind of up and ready on some potential strategies for those sites. It's a little tricky though, because when people generally think data center, like what comes to mind often is like industrial scale, huge, your Googles, your Metas, your huge data centers. They're often like competing on these metrics where they're really trying to be as energy efficient as water efficient as possible. That being said, like if a site that big would want to consult with us, we certainly would. But there's also like just smaller data centers. Like there's data centers embedded in industrial manufacturing facilities that like maybe it's a server room, right? And maybe there's opportunities there, and there's all kinds of different strategies. Some are water cooled, some are air cooled, and there are things you can do from orienting. So like, for example, you want to make sure you have like your hot and cold aisles, right? So if you're not familiar with this, essentially servers are going to pull in air from the front, pull in cold air from the front, and exhaust hot air in the back. So ideally, you want your servers aligned such that all of the backs of your servers are facing into the same aisle, and all the fronts are facing the same aisle. You feed cold air into the cold aisle, and the hot air exhausted through the hot aisle. Things like that can help folks to be more efficient. Every year, well, I don't know how to phrase this, but the temperature, the cold aisle temperature you want to keep in data centers these days, at least in like the enterprise scale, is close to like 80 or 81 degrees Fahrenheit. It's much warmer than you might think, but that's how this equipment is now designed to be more energy efficient. So you need less cooling energy to keep it cool. There's all kinds of cool things happening in data centers.
Yeah, fascinating. I feel like every day I'm learning something new.
I don't know if other questions are coming in. I could share very briefly as well. So what I want to share, I have a brand new project. It just started literally this January. And so this project, we're working for 1 year, and we're partnering with Ramsey and Washington counties. And our goal is to focus on waste reduction. And so we're trying to do about 10 assessments over this next year in those two counties to do waste reduction audits. And then those counties also have a waste reduction innovation grant program. So there's grant funding to help like promote implementation of some of these waste reduction projects. So we are looking to partner with all kinds of businesses, not just industrial manufacturing, but all kinds of businesses that want to just work on, maybe composting, maybe sending waste to animal feed, maybe, whether it's upcycling or maybe it's just actual waste reduction. Like maybe we do a waste sort and figure out, is this actually waste or could it be compost? So we have that project starting literally right now, running for the next year. So it's a great time to talk about it.
Oh, that's exciting. Is that the same like internship process to apply for too if communities are interested in that too, or that's separate?
Well, it is separate. I mean, not to say we could do an intern on one of those projects. It's not impossible, but those are probably going to be handled through general technical assistance.
Okay.
And the benefit there is it's a little quicker, right? You just basically we would come out for a day, we'd chat about, the waste opportunities, maybe we'll do a waste sort, and then we can hopefully move a little bit quicker than the intern program. The intern program is usually for our deeper dives, like if there's a big opportunity that needs a lot of time and effort, that's where we kind of pull in our interns because they can have 500 hours to work on the problem.
Sure. Perfect. Well, thank you. I learned a lot. I feel like I'm writing some notes and have a lot to think about. So I appreciate your time today. I'm going to leave just like another minute if anyone has any questions they really want to get out there. Otherwise, we'll give you these last 10 minutes back to you in your day too. So I'll leave it open if anyone wants to unmute and say a last minute question or comment.
And we did record this, and John, hopefully we can get slides from you and we'll send those out to you all. So if you've got other colleagues or partners that you want to share this with, please do that as well, or follow up with questions offline as well.
All right. Well, thank you so much for having me. I really appreciate the opportunity to chat today.
Yeah, thank you so much. Yeah, have a good rest of your day, everybody.
Thanks, John. Thanks, everyone.
Thanks.
Thanks, guys.